All right, what up, everybody? Coming at you with another physics video today. This time we're talking about Newton's third law of motion, which says that for every action there is an equal and opposite reaction. And we're going to talk about what does that mean for the collision of two objects. Right, so here's an example. You hit a punching bag, the punching bag would also hit you. That's why your hand feels a force. And it would be in the opposite direction you punched it. So when two cars, for instance, run into each other, and let's say these cars are the same size and same speed and everything, then obviously both cars are going to experience the same size of force, just in different directions, right? But what about in cases where the two objects are not equal size or maybe not equal speeds, right? What if one is really big and moving fast, the other is small and moving slowly? Does Newton's third law of motion actually still work? And the answer is yes, it does. Okay, so take, for example, a bug in a car. Okay, the bug is slowly flying along and then it hits the car. The forces by Newton's third law are still equal to each other, right? The bug feels the same force from the truck as the truck feels from the bug, right? And then the time that they collide is also equal, right? They're touching each other for the same amount of time, which means if you know the equation for impulse, which is impulse equals force multiplied by change in time, that impulse has to be equal. So the bug gets the same impulse from the truck as the truck gets from the bug. Right? And if impulse is equal, then you might know the equation. Impulse is change in momentum. They're the same number. So change in momentum is going to be the same. So if we're believing this, then the change in momentum of the bug, which we think is probably going to be pretty big when it gets hit by, it's going to be really affected by this collision, is going to be equal to the change in momentum of the truck, which we don't think is going to be affected too much by this collision. So how can this be? Okay, why is one affected much more than the other? Okay, well, here is the equation for change in momentum. It's mass times change in velocity. So you can see there's two ways that you can write this. You can have a very small mass times a big change in velocity, or you can have a very big mass times a small change in velocity. Right, and that's what you have. Oops. And that's what you have. Okay, starting in 2 seconds. One, two. And that's what you have here. The bug's mass is small, and so its change in velocity is going to be very big. The truck's mass is very big, so its change in velocity is going to be very small. So if you're sitting inside the truck and you run into the bug, you probably don't notice any change in velocity because it's so small. But if you're the bug, you notice a huge change in velocity, right? Here's another example. Okay, a 5 kilogram naughty raccoon is sitting by a 500 kilogram angry bull. The bull is going 20 meters per second when he hits the stationary raccoon. What happens next? What do we know about the force, time and collision, impulse, change in momentum, and change in velocity? So let's start from the fact that we know that the forces on these two are going to be equal and opposite, right? Even though it seems kind of strange that the bull would feel the same force as the raccoon does, but he will. Okay, come off there. So the force must be equal and opposite according to Newton's third law. The time of collision is equal because they both run into each other for the same amount of time. The impulse then must be equal and opposite because impulse is equal to force, which is equal and opposite, times time, which is the same. So the impulse is the same, which means that the change of momentum must be the same because change of momentum is always equal to impulse. The bull is going to change its momentum just as much as the raccoon is, right? And there's the equation for change of momentum, m times delta v. Right, so just like the bug and the truck, you have the same situation where the bull's mass is big, but his change in velocity is small. The raccoon's mass is small, its change of velocity is big, right? So we can say from this that the change in momentum, the total change in momentum is equal. Because what if you added this term to the other side? You would get this right here, that um, the bull's change of momentum plus the raccoon's change of momentum, they would cancel out. One would be positive, one would be negative, but they'd be equal values, so they cancel out, and so the total change of momentum is 0. Okay, so let's put some numbers in here, all right, and I'll just explain what I did. We'll pretend, just to estimate what's going to happen, we're going to pretend like the bull doesn't change velocity at all. Okay, now we know it has to, all right, but let's say it hits a raccoon and they both keep on going 20 meters per second. Well, the raccoon's change, the mass of the bull is 500. The mass of the raccoon is 5. The raccoon's change in velocity would be 20 because it was sitting there on the ground. Now it's going 20 meters per second with the bull, which means if you do the math here, that the bull's actual change in velocity, okay, would be 0.2. Okay, so it would, the bull after hitting the raccoon is going to be going about 19.8 meters per second. Okay, and that's an estimate because we put 20 in here. All right, maybe we should put it 19.8 in there and see what happens. But the bull's velocity changes very little. The raccoon's changes a lot. Okay, and that gives you an idea of the effect of Newton's third law on collisions. If the objects are the same size, they're going to have about the same change in velocity. But if they're different sizes, the big one is going to have a much smaller change in velocity, and the small one is going to have a bigger change in velocity. Which is why the small thing is usually the one that gets the most damage in a collision. All right, so that is Newton's third law on collisions.